Hello everyone and welcome back to another episode on complete reference to CUDA programming. In this session, we'll talk about performance metrics of parallel computing. So there are two main goals to be achieved with the design of parallel applications. One is performance, other is scalability. So let's try to understand first what is parallel computing. We'll try to understand parallel computing first and then we'll see how these performance metrics utilized to measure the performance of parallel applications. So again, let's revisit our same real life application or task, that is digging 32-meter big hole. The same application we have discussed a few episodes back. I think first or second episode we discussed this particular task. So this is the scenario where task is digging 32-meter big hole. This is the first one, and here we are having only one resource here, and let's assume the efficiency of that resource is 1 meter per hour, and based on this complete scenario, the entire time required to complete that task will be 32 hours. Now in this case, if I increase the number of resources from 1 to 2 here, now the overall efficiency becomes 2 meter per hour, because for one resource it is 1 meter per hour, so for two resources it will be 2 meter per hour. Now overall task can be performed in 16 hours. Earlier it was taking 32 hours, now it is taking 16 hours. Same way, if I go on increase the number of resources here to 4, then the overall efficiency becomes 4 and the total time required will be reduced to 8 hours. Now if I increase the number of resources to 8, the overall efficiency becomes 8 meter per hour and total time required equal to 4. Now what is happening here? We are given a task and we are having more number of resources, and that number of resources getting the task divided among themselves. And that is what happening in the parallel computing. So what is parallel computing here? Type of computing where many, we can say, calculations or processes are carried out simultaneously. So you can see here we are having two resources in this particular example where they're working in parallel, and that's the reason overall efficiency is increased and the overall time is reduced. So ideally, what expect in parallel computing, given any task T, we are going to distribute among multiple resources. And in parallel computing, resources are nothing but the core. So resource 1, resource 2, and so on will be having n number of resources. And these resources can execute that partial task parallelly. And that's the reason overall time required to perform that task is reduced. Fine. Now same thing we can relate to your computers again. So I'll be having here again a task T where task is performing matrix multiplication of 16 by 16 matrices, right? So resource here is nothing but number of cores here, and in this case I'm having single core. Now assume that we are having efficiency of 1 row per minute. So if you recall, the matrix multiplication task is going to be like this. So I'm having a matrix A, and which will be multiplied to matrix B, and so that I'll get the matrix C. I'll not go into the details of how to perform this computation, but let's say to compute output or resultant one row of your resultant matrix, it takes 1 minute. Right, to compute the output matrix first row, it takes 1 minute, or for all rows it takes 1 minute per row. Right, that is the efficiency of this single core CPU now. And if you see, overall time required to perform this particular task will be 16 minutes. Right, so this is going to be the sequential execution because I'm having a single core. So time required to perform the task using one core will be 16 minutes. Now I'll keep the task same, but I increased number of resources to 2. That is, I'm having a dual core CPU now. Now I'm having 2 cores available, and every core's efficiencies, they can compute one row of output matrix per minute. And now if I'm having two such computing resources, so combined efficiency becomes 2 row per minute. And in this case, now overall time required will be 8 minutes because we are having two resources. Same way, if I go on increase number of resources to 4 here, so quad core is nothing but the 4 number of cores. So in this case, the overall efficiency becomes 4 row per minute and the overall time required will be reduced to 4 minutes. Same way, if I increase resource to 8 numbers, then efficiency becomes 8 row per minute and overall computations can be performed in only 2 minutes. Right, so you can see there is a relation between number of computing resources and overall time required. And whenever you write any parallel program, you need to communicate your results in terms of these performance metrics. That means how better your parallel version is performing compared to your sequential version. And to do that, we have two parameters, performance parameters are there. We'll discuss in a while here. Now, what do you mean by this performance? It is nothing but simply the capacity to reduce the time to solve the problem when the computing resources are increased. That means as we go on increasing the computing resources, the time required to solve that problem must be reduced, and that is nothing but the performance. Another goal is to be achieved is scalability. So scalability is nothing but the capacity to increase the performance when the complexity or size of the problem go on increasing. That means if my input size is n now, in future if that size becomes 2 times n, then in future it also becomes 4 times n. So in case of this increasing the problem size, whether your parallel solution is also giving the same performance or it is reducing, right? If it is reducing with increasing number of resources or input size, then we can say that it is poorly scalable, right? And if the performance is increasing with input size, then obviously we can say it is good scalable, right? So these are the main goals we have to achieve. Now, what are the factors that are limiting to the performance and scalability here? There are some architectural limitations are there, that means hardware limitations, and there are some algorithmic limitations are there. So first, let's focus on architectural limitations. So first one is the latency. So as we discussed in some previous episodes, that latency is nothing but amount of time required to fetch data from main memory to the processor. And if that latency is more, that means your performance of your application is limited by that the time it takes to fetch data from main memory to the processor, right? It has nothing to do with your number of cores available, because your application is like it performance depends on how fast you can fetch the data. Then bandwidth is another parameter where we can say amount of data in one go can be fed to the processor. If that bandwidth is less, that means at the same time we are feeding less amount of data to the processor, and that's why your performance can be limited. So there are some hardware limitations are there, so which are going to restrict the performance of your application. Then data coherency, how we store the data, right? So if you are having cache memory, which frequently data can be stored into the cache memory, that kind of you can say solution is not available in your hardware, then definitely it is also limiting factor for your performance. Then another limitation factor is memory capacity. So if you are having limited main memory, so and if your data or your program cannot fit into the main memory, then some portion will be stored into the hard disk. And if the processor is expecting data from the hard disk, which takes a longest latency. We have seen in previous episode. If you're not able to recall, I would recommend to go back and revisit that previous episode where I explained the memory hierarchy. And out of this all memories like register memory, cache memory, main memory, and hard disk, the hard disk is having the longest latency. And if most of the time your data is sitting in your hard disk, so it takes longer time to fetch the data toward the CPU, and that could be the limiting factor for your application's performance. So these are the architecture limitations are there. We are not going to play around with these architectural limitations, but rather what is in our hand is algorithmic limitations. So it is possible that application is inherently sequential. That means there is no scope for the parallelization, right? There are some applications where we cannot make them parallel. For example, we have the computing pattern, like input of first statement is output of first statement is input to the second statement, and output of second statement is input to third statement, and this dependency carried on. Now, if you have these sort of computations, no matter how many parallel computing resources we are having, still the computation itself is sequential, so we cannot parallelize it, right? So if we are having some algorithm which is having limitation of parallelism, then we can call it as a algorithmic limitation. It is possible that your algorithm is designed in such a way that we have to perform the communication between multiple resources frequently. And what happens, the communication in case of parallel computing is nothing but the overhead, because if two computing resources are communicating, that means they are sharing the data, and while that data is being shared, the computing resources are sitting idle. That means no operation is being performed. And if your computing resources are sitting idle, that will result into your poor utilization of your computing resources, and that could be the limiting factor for your parallel application. The third algorithmic limitation is synchronization frequency. If there are too many synchronizations are there, right? We'll discuss what are the synchronization in subsequent episodes. But synchronization, you can consider as of now, it is kind of speed breaker for your parallel execution, right? So more the synchronization terms are there in your parallel execution, which will force your execution to be executed in specific order, then that could be the limiting factor. Then we have poor scheduling. Poor scheduling can be also a limiting factor, because let's say, what do you mean by poor scheduling? If we take this example here, what we were visiting in previous here, uh, for example, what we are expecting, if this task is to be divided into two number of cores. So what we can expect, maybe the first 8 rows will be performed by core number 1, and next 8 rows computations will be performed by core number 2. So that is our assumption. That is, the computations are equally divided among these two cores. Now, if I divide that in such a way that core 1 is getting only one row to perform, and core 2 is getting all remaining 15 rows to be performed. So 15 rows are provided for core number 2. So this is imbalanced load distribution, right? So in this case, even though I'm having two number of cores present, but unfortunately load is balanced in such a way that first core is getting less work and second core is getting more work. In this case, overall time required will be 15, because core 2 got the highest job, that is to perform computations for 15 rows, and we know the efficiency of core 2 is 1 row per minute, so it takes 15 minutes to perform this task. And during this time, well, C2 is performing all these operations, C1 will be sitting idle. So that sort of scenarios, we call it as a imbalanced load or poor scheduling. That could also limiting factor, right? So based on this, now we have some performance metrics, out of which we'll focus on only first two, and later on we'll be focusing on remaining metrics as per the necessity. So let's focus on first thing, that is speed up. So speed up is nothing but it is a measure of performance again, and it measures ratio between sequential execution time and the parallel execution. So we'll be having a given program, we'll execute sequentially first, we'll record its time, and then we'll parallelize it, right? So we have not discussed so far how to parallelize, but let's say we'll parallelize it using p number of processors or cores, then amount of time required in parallel and amount of time required in sequential, if you take that ratio, that is called as speed up. So if you say this application here, this is the time in sequence for required, that is called as sequential time, because we are using a single core here, right? So this is sequential time which takes 16 minutes. Now I'm having here dual core, that is two cores are present, and in that case it takes 8 minutes of time. So how speed up will be calculated? So S of 2 indicates speed up with two computing resources here, that is 2 here, and equal to sequential time upon parallel time. So sequential time is 16, and in this case the parallel time is 8, and 16 by 8 gives you 2. That means in this scenario I got twice speed up, right? So my application running twice, 2 times faster than the sequential one. And this is how we represent 2x indicates 2 times better performance. In this scenario here, we are having sequential runtime will remain same, that is 16, and parallel runtime is 4 here. And based on the speed up definition, 16 by 4 becomes 4x. That means this particular scenario giving me 4 times better performance compared to the sequential one. And similarly, for this scenario, the speed up is going to be 8 times better compared to the sequential one. So that is called as speed up. So very often, whenever we are writing any parallel program, we try to communicate our results in terms of speed up. That is how fast your program become compared to your sequential version by using multiple computing resources. So that is called as speed up. Now second one is we are having efficiency, and it is nothing but the measure of the usage of computational resources. We need to also put emphasis on how efficiently our computing resources are being utilized, right? And it is defined as speed up upon total number of processes, or we can say computing resources here, right? So we know the definition of speed up, that is sequential time upon parallel time, and divide by we are having this number of processor or number of computing resources. Now let's go back and try to calculate efficiency in this case again. So here we got speed up is 2 times, and we got the speed up using 2 computing resources. So efficiency becomes speed up upon 2, that is number of cores, and becomes 100. That is 100% efficiency. That means my all the computing resources are utilized effectively. Now in this case here, my speed up is 4, and total number of processes or cores are also 4 here, so it becomes efficiency here also 100. And in this case also, the total speed up, that is 8 divided by total number of cores are 8, and which is also again 100%, right? So efficiency here we are getting 100%. We'll come to the point why we are getting 100% efficiency, or what are the possibilities or possible scenarios where we'll get efficiency less than 100. Okay, so that's it about speed up and efficiency. Now let's talk about finally, that is Amdahl's law, and which is very important law in parallel computing, right? And it tells about what is the maximum speed up we can achieve in case of your parallel application. So to understand this Amdahl's law, let's first of all try to understand a typical program. A typical program is divided into different components. Some portion of your program will be completely sequential. That means the computations cannot be parallelized. It is not like that. When you write any program, it is 100% parallelizable, right? It is possible that some portion of your program cannot be made or cannot be executed in parallel. That we call it as a sequential portion of your program. There are some you can say portions in your program which can be parallelized, that we call it as a computation that can be realized in parallel. And there are some computations related in your program that are related to communication, synchronization, or initialization, that has nothing to do with your computations, right? So sometimes we are, in case of parallel programming, we have to communicate between multiple computing resources. Sometimes we have to be in synchronized with all remaining computing resources, or sometimes we invest some we can say time in initialization of those resources, right? So that comes under communications. And if you talk about the speed up, is can be again written in terms of all these parameters as a sequential upon parallel is decomposed as sequential component plus parallel component here, right? So that is nothing but the total sequential time. And in the numerator, denominator, we are having sequential portion plus this is the parallel portion plus this communication, right? So you can see here parallel portion is divided by p number of computing resources. So accordingly, the overall time will be reduced here, right? So speed up is simply represented in terms of this formula. Now let's say f is a fraction of the computation that can only be realized sequentially, that cannot be parallelized. So I can write that fraction in terms of sequential component upon total component, right? So sequential divided by we are having sequential plus parallel, that is called as a fraction of program that can be realized only sequentially. Now this fraction will be always between 0 to 1 because we are taking sequential portion and we are dividing by total portion. So it will be always in 0 to 1. So if it is, let's say 0.5, so I can say that 50% of the program is sequentially and executed and 50% can be parallelized. The fraction, if it is, let's say 30%, so I can say out of entire program 30% is will be executed sequentially and remaining 70% can be parallelized. Now based on this, now we have Amdahl's law that tells us that maximum speed up that a parallel application can attain with p process is given by, so sp equal to, which is less than equal to 1 upon f plus 1 minus f by p, right? So if let's say we are having the total you can say sequential component is 0. Let's assume ideally we are having there is no sequential component or computation in your program. Again, this is very hypothetical situation, but let's see what happens. The sequential fraction becomes 0 here, this term becomes 0, 1 minus 0 becomes 1, and 1 by p becomes p. That means speed up will be p. That means if I'm having two let's say p number of computing resources, then speed up will be p. And that is what happening in our previous matrix example. Here we are having two cores and we assume that the entire this computation can be executed in parallel, right? There is no sequential component, right? So with that assumption, we got here 2 times speed up. When I'm using 2 cores, I'm getting 2 times speed up. When I'm using 4 cores, I'm getting 4 times speed up. And when I'm using 8 number of cores, I'm getting 8 times speed up. Because we have not considered the sequential fraction of your program. And that's the reason we are getting speed up equal to number of cores. But as I mentioned, this is ideal situation. But in reality, when we write any program, there will be some components that are related to communication. There will be some components related to your synchronization, and there are some instructions in your program that cannot be made executed in parallel. So that's the reason there will be always some portion that to be executed in sequential, and that's the reason your speed up will be always less than your total number of cores. Or in short, what we can say is that as per the Amdahl's law, the maximum speed up that a parallel application can attain with p processor is p, right? So that's it for this particular episode. In this episode, we have discussed different performance metrics and to be a very important law in parallel computing, that is Amdahl's law. So next, we'll start talking about CPU limitations of multi-core CPU and GPU architectures. So stay tuned for that. Bye-bye.